Hello everyone, I'm very glad to stand here to give a talk to you. Today my topic is about PV monitoring based on linear regression. I'm introduce myself at first. My name is Wang Bo. I have been working in Baidu for 4 years. My work focuses on anomaly detection, alert analysis, and troubleshooting. These are 3 important aspects in AI ops. Today, I'm going to introduce our work on anomaly detection for PV monitoring. PV is a short form of page views. In our daily work, we use PV to refer to various requests. For example, the request that the user sent to our service, or the request that from one system sent to another system. PV monitoring tracks the number of the page view or requests in a given time interval. The PV number is one of the golden signals of our service. The change of PV number can indicate many types of the failure. For example, when a fiber of an SP breaks, some of the user will be disconnected from our service. This would cause a decrease on PV number. We call this decrease as a PV loss. Second, when a model in our system goes down or its business logical implementation has bugs, part of the function will not work properly. It also creates PV loss. PV number increase may not be good thing either, because it may be caused by coolers or attacks, or reliability engineers need to know the anomalies of PV number as soon as possible in order to take actions to stop loss or prevent potential loss. Therefore, anomaly detection on PV number is very important to maintain high system availability. However, this is not a trivial task. The difficulties of the PV monitoring relate to the following facts. First, many PV number curves has a periodic pattern. Suppose there is a PV curve directly from the end user's request, because most users will go to bed during the nighttime, and the PV number will drop in the night and increase in the daytime. When we try to detect anomalies on this PV curve, we need to consider the time of the day. So we cannot set a fixed threshold on the detector. And this means the anomaly detection on PV number is contextual. What makes the things worse is that the local fluctuations also change with time. We observe that the relative local fluctuations is lower in the daytime and higher in the nighttime. This behavior makes many ratio-based detection algorithms to produce incorrect results. Second, our engineers have mathematical concern about PV rise and PV drop. The reliability engineer concern more about PV drop, while the safety engineer care more about abnormal rise. The asymmetric concern forces us to find algorithms that know exactly whether it is rise or drop right now. Third, the PV number will have a level shift when the system upgrades or the business logical changes. It would be better that the algorithm can keep up with the change automatically without any manual intervention. As a summary, the anomaly detection on PV numbers must be contextual. It's able to differentiate rise and drop, and it's adaptive to the level shift. Our algorithm is composed of 2 steps, predict step and detect step. In the predict step, the algorithm forecasts a PV number for the current time. By subtracting the predicted number from the observed number, we can get a residue. A positive residue means a PV rise, and the negative ones means a PV drop. Of course, the forecast must be contextual and adaptive to the level change. In the previous slide, I mentioned that the local fluctuations on PV numbers are also contextual. This means the scale of the residue still changes over time. So in the detect step, we transform the residue into a contextual free value and then apply anomaly detection on this value. Next, I will introduce the detail of 2 steps. Our first try in the predict step is moving average. Let's take a look at the moving average algorithm. The PV number data is defined as follows. T is the time of data. which is from 1 to n, and yt is the value of the PV number at time t. Moving average computes the predicted PV number y hat t as the following formula. Here, W is the length of the window of moving average. In fact, y hat t is just the mean of all the yt's in the window. The window slides through the time series to detect the anomalies. The window, moving average is widely used in many fields, but the finger on the right side shows some example. In the top 3 fingers, the blue curves are the actual PV number, and the orange curves are the predicted PV number. In the first finger, there is a drop on the PV number, but the predicted number lags behind the trend and missed the drop. The second finger shows a downtrend. The predicted value indicates that PV number has been dropping all the time, so it is easy to produce false alarm on the downtrend. The third finger shows a PV number with spike caused by attacks. The residue of the PV number and the predicted number is shown in the first finger. Because the predicted number lags behind the actual number, the residue becomes negative every time when the attack stops. This leads to a lot of false alarms. The reason is that for moving average, a PV drop and the recovery of the rise is equivalent. The shortcomings of moving average relate to its lag behind the actual trend, so we try to consider the trend in a relatively short window. The trend can be simplified as linear. Therefore, our second try is linear regression. Linear regression fits the PV number in a window with a linear equation, as shown in the figure. On the right side, the blue curve is the raw data of a window, and the right line is the predicted line. The right point is the predicted value of time t. To search for the best equation, linear regression introduces a loss function. The best equation pairments k and b should be minimize the loss. The loss function is least squares, which is the sum of the squares of the residue. Unfortunately, linear regression still has its problem. Let's see an example on the right side. The upper finger shows the result in a window. The blue curve is the PV number, and there is a abnormal rise near the right side of the window. The blue curve is the PV number, and there is the line fits by the line fitted by linear regression is the right one, and the pink line is the ideal result. Obviously, the right side of the right line is pushed up by the right abnormal rise. The lower finger shows the PV curve and the predict curve. We find that the prediction curve in orange still has undesirable fluctuations. Linear regression uses the least squares as the loss function, but the square expands the impact of the abnormal values. This forces the fitting line to move towards the abnormal values. This is why linear regression is susceptible to abnormal values. To solve the problem, we have suppressed the impact of the abnormal values. One idea is to change a loss function from least squares to least absolutely deviation. The new loss function removes the square from the residue, and the impact of the abnormal values is reduced. Unlike the least squares, the least absolutely deviation does not have a closed form solution. So we apply the iteratively reweighted least square approach. This approach adds a weight to the square of each residue. Based on a set of the initial weights, we can solve the equation to find best k and b. This will derive the predicted value and the residue. Then weight is updated to the inversion of the residue. Now the new k and b can be obtained from the updated weights. This procedure will be repeated several times until k and b converge. This iterative procedure is sensitive to the initial weights. If the initial weights are not chosen properly, the result will converge to a bad place. The finger are two examples. In both fingers, the light blue curve refers to the same PV curve. Dark blue line of the fitting line from the regression. Pink star refers the points with the large initial weights. We can see that the different initial weights produce totally different regression results, and we can definitely want the result in the second finger. So we need a way to set initial weights properly. The observation of the PV curve shows that the slope of tangent line of two adjacent points change slowly. The slope is actually the k in our regression. Therefore, we can compute the initial weights from case of the previous points. The mechanism stabilizes the regression most of the time. But there are still a few cases that the iteration results in bad k and b. To deal with these corner cases, we compute the z-score of k based on its previous values. If the z-score is very large or small, the iteration result is dropped, and the best previous k is used instead. This is the prediction result by our robust linear regression. The blue curve is the PV curve, and the black curve is the prediction result. We can see that our method successfully ignores the abnormal rise and stick to the desirable baseline. Based on our prediction, we can compute that the residue by subtracting predict value from the observed values. The residue cannot be directly for anomaly detection because the normal amplitude of the residue change is different for different curves at different time. This means we would need to set a lot of threshold in order to get a precision detection. Usually, when the PV number is large, its normal amplitude of residue is also large. So our engineer tried to use residue percentage to solve the problem. Residue percentage is the ratio of the residue to the predicted PV number. Surprisingly, this still doesn't work. The data shows that when the PV number is small at the nighttime and the normal amplitude of the residue percentage become larger than at the daytime. So we still have multiple thresholds for different time. To understand the behavior of the residue, we model the PV number using the probability distribution. PV number is the number of the views of requests received in a fixed interval. This just falls into the scope of the Poisson distribution. Poisson distribution models the number of the random events happened in a fixed time interval. From this perspective, we can regard the observed PV number yt as a random variable of the Poisson distribution, and the predict PV number y hat t becomes the expectation lambda of the random variable. The probability of distribution function is shown in the formula. Suppose we focus on the PV drop. We need to pick a threshold C such that probability of yt smaller than C is smaller than a very small value p. The probability of the yt smaller than C can be computed by summing all the probability of the yt smaller than C. So a proper C can be founded by gradually summing up the probabilities starting from 0. Usually, the PV number at the scale of the several 100,000. Search for C in this way would be computation intense. But when the expectation of the Poisson distribution is very large, normal distribution becomes a good estimate. The expectation mu and variable sigma square of the normal distribution both equals to the expectation of the Poisson distribution y hat t. According to the normal distribution, C can compute it by subtracting m times sigma from y hat t. Actually, we can compute a better value z, the quotient of the residue divided by sigma. Now, the detection only needs to compare z against minus m. Here, m is decided by p only. P is the probability threshold and is free from the influence of the PV number scale and time. The number of z is called z-score in statistical hypothesis testing, and the procedure is actually a z-test. This amazing conclusion can explain the question why residue percentage doesn't work. When using residue percentage, we try to find the threshold R. If the residue percentage is smaller than minus R, an anomaly is founded. If the percentage threshold R is equivalent to the z-score threshold M, so M equals to R times square root of the predict PV number Y hat T. Because M is not affected by time, it remains constant during day and time. This means the percentage threshold R at night should be equal to the R at day times the square root predict PV number Y hat at day divided by Y hat at night. Because Y hat at night, Y day is larger than Y hat at night, the percentage threshold R at night must be larger than R at day. In one of our curves, our engineers to set a percentage threshold at day to 4% and to 8% at night. Based on their experiments, we observed that the PV number of these curves at day is roughly 4 times the number at night. This indicated that the probability model is consistent to the engineer's experiments. This page shows the result by our detector. The finger above is the raw data and the predict value. The right point are the drop detected by this score, and the finger below is the z-score value, and the right line is the z-score threshold. We can see that this score threshold remains constant at all time, and PV rise and drop are separated clearly. The algorithm is finished, but evaluation is still a problem because labeling the curve is time-consuming and tedious. So we built a labeling tool to help and the labeling. The tool is web-based and open source on GitHub. You are welcome to access the preview version at curve.baidu.com and download the source. Our evaluation result indicates that precision is more than 80% and the recall is more than 95%. As a summary, we propose an anomaly detection method for PV number curves. The algorithm consists of 2 steps, prediction and detection. The prediction step leverages Rubin's linear regression to predict numbers. Rubin's linear regression uses least absolutely deviations as loss function to reduce the impact of the abnormal rise. And then we solve the problem of the multiple solution to obtain the ideal result by prior knowledge. The detection step models the observed PV number using Poisson distribution. We transform the residue into this score, and this score is free from the impact of time. At this point, the contextual detection problem is reduced to an easier contextual-free detection problem. Okay, that's all.